Oh, yeah. That's what I forgot. Where are you? Oh, come on. Somebody did what they're supposed to do, which is really annoying. All right. All right, guys, any more homework questions before we get
Yes.
where are you at? There you are. Did you turn it?
On 3.9.
Which one is it? There we go. 15. Oh. All right. 3.9. Is that the light post problem?
Yeah.
Yeah! All right. Ugh. All right. How many people does this look familiar to? Anybody? Anybody else?
Familiar in a way that I know that I can't.
No, as far as you've tried it. You've looked at it. So a lot of you guys did not raise your hand, so I'm not going to say too much about this then. Street light, top of 15-foot tall pole. A man is walking away from the pole. Doesn't matter which direction, no. With that speed, along a straight path, blah, blah, blah. If you drew that picture, what would it look like? Just draw the picture. It doesn't have to be a dude. You can have a stick for a dude, stick for a light pole. Light pole's taller, right? That's important. Can you guys just take a second and draw that picture? Here, I'll get it started. All right. It's going to take all my artistic ability that I have. Light pole. Okay. All right. Let's make that taller. Taller light pole. Okay, there we go. Okay, there's a light pole. Where's the dude? He's walking away from it, so let's put him over here. He's shorter than the light pole, yes. Okay, this is not to scale because it doesn't really need to be. Where's this dude's shadow? Wouldn't it be down here, right? Because here's the light. Exactly where would his shadow stop? I would have determined that. Don't overthink it. Why does his shadow exist? Because the light can't go through his body, thankfully, or else he'd be one freaky dude.
Triangle off the top
Yeah,
line.
so wouldn't his shadow end there? Right? Again, not drawn to scale, and somebody sat on my triangle, but we'll be all right. Does that make sense so far? I mean, that's why a shadow exists, because it goes, hits the head, and then anything below the head is blocked. So that's why you have a shadow, and the light goes up to the top of the head. Straight line. I like it. All right, so now you just got to identify some variables. Shit. Hit the right button. There we go. Is this a variable? No, it's a light pole. It's 15 foot tall. This is 6. Okay, those don't change. Those are fixed. What is changing? 2 things. Yeah, what's this? Yeah, we can call it X. What's it represent? Good. And what's regulating how quickly that's changing? True, but what physically in English? How fast he walks. Good. So I know what dx dt is now from what they told me in the... Do you guys see what's happening? This is how you kind of construct this. So not only do you have to identify variables, you have to really understand what the hell they mean physically. So why is this changing? Because it depends on how fast he's walking and whatever the hell, I can't remember. So what's this? I will accept a few different answers. What's that?
His shadow.
His shadow. I like it. The length of his shadow. What can I call it?
2/3 x.
We're getting there. It's a little far ahead of us. Any other variable, exactly. S for shadow, but you know me, don't you? That S looks like 5 and 5 looks like S, and they both don't look like anything. So I'm going to use Y. Get over there. You can use whatever variables you want to, right? Okay. So if you were not able to get to this point, you had 0 chance to do this problem. So this is the diagram representing the physical situation. What's the equation relating everything? What idea relates everything I've got there? Yeah, this triangle and this triangle. How are they related? They're similar triangles. Okay, what the hell's that?
Oh, they have the same angles.
I am asking you.
Yeah, they have the same angles.
Same angles. Do you want to bring angles into this?
Not really.
No, dear God.
They are.
The ratios of their sides have to be, I heard it over here, proportional, right? Whatever 6 to y is, all right, let's try, let's be careful. Like, if this was 6 and this is 12, this is y, this would be 2y, yes?
Yeah.
Because it would be twice as big. That's all this is the bigger triangle is some multiple of the smaller triangle. Therefore, all the sides will reduce to the same thing. So 6 to y equals what? Small triangle up and down side to small triangle left and right side equals
15x plus y.
yes, 15. What's wrong with this? Yeah, because that's not a triangle, is it? That's a freaking trapezoid. Oh shit, now it's a triangle. All right, that's all I'm going to say. Because now you attack that with calculus. All right, well, maybe not immediately. I would simplify that first. You can simplify that a lot. Okay. Something interesting happens. There is a number they gave you that is not important in this problem. All right? Because we're evil, math people are evil. Let me see if I can, here's a general idea. Okay, this is what I was showing somebody else. Remember that problem on the test? That was all about the area of a circle, right? What do I get when I take this guy's derivative? Not quite. There it is. If I just tell you this, are you able to tell me what this is? Nope. What else do I need? Then I've got to go back, plug some shit in, figure out what R is at the snapshot time. Are you guys with me? Why did I have to do anything with the snapshot time? Because when I took a derivative, I got an extra freaking letter floating around. Damn it! Now, what if it was the circumference that I'm interested in, not the area? What is this guy's derivative? I'll do this side again. Whew. Almost. There it is. Right? I'm not taking respect to R, I'm taking respect to T. Do I give a shit about the snapshot time? If I tell you the radius change, do I need to know anything else to figure out the circumference change? Nope. So it doesn't matter at what time this occurs. No, I really hope you guys sort of get what I'm saying. Set up the formula that relates the variables, take the derivative, and then say, oh shit, I don't know that. Let me go do it. Here, I do it. There's not a damn thing I don't know. If they told me this was 3, I plug that shit in, I'm done. I don't have to worry about the snapshot. What if they told me at a time when the radius is 11 square root of 7? Would that matter? Does that matter? No, it doesn't matter what that is. Okay, maybe. I love you guys. Maybe? Not really? Screw you, Jeff? Okay. All right, I don't know what else to do. So it's remember, I keep saying that snapshot time. At a time when this side is 40 meters, or at a time when the angle is 60 degrees, or whatever. Why did they give me that? In case there is a variable still floating around after I take a derivative, I need to know what the hell to plug in for that. If there isn't, I don't. That kicks so much ass. Isn't that... all right, that's enough. All right, somehow that relates to this problem very directly. So I highly recommend you simplify this. Do you want to do implicit differentiation as it is right now? Do you understand how disgusting that would be? Not only are my variables on the bottom, they're also on the bottom doing stuff with each other. That sounds... it's just going to be that kind of day. I had a shirt that I'm going to have to make that has a few different ways to think about it. All right. Get out of here. Man. Anything else from homework? Yes. Oh, real quick, before I forget, what was that one? That was 15. 18 is almost the same. It's very similar. It's going to be just a little more complicated. You will have to worry about the snapshot. I'll tell you that much for number 18. You will have to worry about this. So that's a little clue. But they are very similar, pun intended. 41?
Yes.
Oh, yeah, this is a good one. Ooh, yeah. Oh, okay. Can you guys draw that real quick? If you haven't done this yet, can you draw? All right, there it is, right? Pew. Is that cool? One side, the other side, the angle between them. As time goes by, what is changing about this triangle? Right? The angle is changing, correct? Is anything else changing? The third side's changing, right? Do we care about that? It seems like right now we don't. So the angle is definitely changing, which makes sense. This is why they told me this, right? But these are constant, yes? Okay. So, the whole idea here is, what formula do I set up for this? So let me draw. Oh God, it's supposed to be about the same. Okay. So if this is A, this is B, this is angle C, and this is C, and this is A, and this is B. Oh yeah. Oh boy. Isn't that basically the situation? What's dA dt going to be? What did we just say? What's dA dt going to be? 0. Because those sides aren't changing, yes? But this is the general idea of this, yes? It just so happens that dA dt is 0 because it stays 12. What else is 0? dB dt is 0. Okay, I like it. What is the relationship then that relates these things especially? And the question really is about this other side, correct? Okay. So as this angle, what is it, decreasing or increasing? Increasing. As that angle increases, isn't this side getting bigger, of course? Whereas my hands are not growing as I do this, right? Too bad for that lawyer on It's Always Sunny. Open this up. My hands are staying the same, but this is obviously getting bigger. Yes? This is a high-tech example. Okay. What is the relationship? Is this a right triangle? Necessarily. No. Maybe at some point it is, but it isn't in general, right? So what relates these things? Law of cosines. Law of cosines. Does anyone remember law of cosines? What's the Pythagorean theorem? C squared equals A squared plus B squared. It only works for right triangles. Law of cosines has an extra term that is an adjustment if it's not a right triangle. Yes. 2ab cosine, in terms of what I've got here, cosine c. Yeah, you can make this theta if you want to. You want this to be theta? It doesn't matter. Does that look familiar to anybody? I mean, that part definitely looks familiar as shit. What's really beautiful about this is Pythagorean theorem is true in a specific situation. So the more general situation, better revert to Pythagorean theorem in that specific instance. And this is just an adjustment. If that's theta's 90, what's this adjustment become? 0. Then it's Pythagorean theorem. Pythagorean theorem. Okay. So now you do derivatives. What's dA dt again? Oh, interesting. So when you do derivatives, some nice things happen. All right, that's enough of that. Yeah. Anything else? Okay, all right. Those are some of the better ones. I like those. Those are some of the more interesting problems. Okay, all right. So we have one thing from section 310 to finish, one idea. Oh, my poor paper. So we did linear approximation last time, which I know that we've set up something. It makes it feel like it's brand new. It is old shit. It is old shit. Let me do this real quick. You're all like, do whatever you want to. Man, can I find it real quick? Where are you? There you are. Yes, good. Can you find the tangent line to this function at x equals 0? Right? That's a chapter 2 problem, really. Well,
Is that 1 plus y or 1 plus x?
1 plus x, sorry. That'd be really freaky. It's not a, so okay. Tangent, yeah. Equation of the tangent line. This needs to be right now. You should see this problem on a test or something and go, oh, thank God. Oh, thank God. You have to, because this is like one little step away from algebra stuff, right? What 2 things do I need to figure out the equation of a line? Slope? How do you get the slope? Yeah. So what's f prime? I like it. What's funny is, that's not funny. Once we do related rates, you guys start to overthink certain things. But what am I doing? The derivative. Good Lord, man. What did I do this morning? Did I take too much meds or too little? All right. What am I doing the derivative with respect to right now? X. I love it. This is not rates of change over time, right? So be really careful. I understand. You think that we learned something new and it's the new way to do things. No, that's just a side note. Related rates are just a side note. So what is the slope at the point that I'm interested in? No. I like how confident you were with that, though. There it is. Because this is 1, yes? All right, and what's the other thing I need for an equation of a line? I got the slope, I need a point. And what's the point? That doesn't sound like a point. 0, 1. Y minus y1 equals m times x minus x1. Y minus 1 equals 1/2 x minus 0. Y equals 1/2 x plus 1. Is everybody with that? Isn't this old? Isn't this like from early chapter 3? When everybody agreed with me? Isn't that what we freaking did last time? Yes, that's what we did last time. What did it look like last time? It looked like this. But isn't this y minus y1 equals m, x minus x1 is... Okay, I really, really want you to understand this is not new. This is not new. It's just a way to capture everything in one line. The slope is the derivative. Okay, then don't put m, put derivative, right? The y1 is the function evaluated at the point. Okay, so don't put y1, put f of a. So that's all that does. It's old shit. Okay. Go away. Go away. Okay, so that's linear approximation. It looks new. It isn't. Okay. And the other thing we got to talk about differentials. These little dudes here, those are differentials.
Is this still 310?
310, yes. It's the last part of 310. Tell me this. What was another way to write this? F prime, right? Right, yes? Or y prime, so let's say f prime of x. Is that cool? So then isn't dy equal to f prime of x dx? So watch this. I really want this to make sense. What's the whole idea of slope? If the slope was 1 over 2, what does that mean? If I move over 2, how much do I go up or down? If the slope is 1 over 2, I move over 2, go up 1, right? So I always go up half as much as I went over because the slope is 1/2. Is this cool? When I teach slope, I teach it as being like an amplifier or a whatever the opposite is. Because it's y changes half as much as x if the slope is 1/2, right? Or if it's 2, it really does amplify. Every change in x gets amplified by 2, gets multiplied by 2. Okay, stay with me. This is talking about if I take a very crazy small step in the x direction, how much will the y change? Well, it's dependent on the slope. Maybe? Yeah, this is all we did. So the change in y is the slope times the change in x. That's all it says. But the little, what does this indicate in front of the x and the y? How big of a step are we taking? Infinitesimally small. In fact, these are sometimes called infinitesimals. Right, sounds like a really weird superhero group, but infinitesimally small step. Okay, you guys with me? Okay. So this is why this is exactly true. Because what happens if I have a function and I take a big step? Now here's the tangent line at a point. Yes? If I take a big step away from this, is the tangent line true about the function anymore? No. But if I take the smallest step possible, then it is still true. Because it only works right at the point truly. Okay, maybe I won't go too far down that path. Okay. So that's one way to look at things, and this only works locally. So what works on a larger scale? Well, that would be this stuff here. Oh, let me see. I don't want to tie this together. Okay. All right, let's do this. Okay. Isn't that true? Okay. So isn't delta y equal to f prime of a delta x? Right? All right, this is roughly true. So maybe not the greatest way to capture this. I've got a picture I want to show you. Page 254. Bam. All right, let's do this without destroying my camera. I don't care if the SD card, okay. All right, so this is what I was saying earlier. This is a big step, right? Delta x, whenever you see the triangle, I think big step. So this is what I was trying to say earlier with my crappy little drawing. Here's a computer-generated drawing. So here's the tangent line. If my dx is actually a big step, then obviously the tangent line is no longer a good approximation, yes? This connects with that linear approximation stuff. It only works to within so much. If you only want the error to be so much, you can only go this far away from that point that you created the tangent line around. Right? Okay. So if I go over delta x, then the actual function changes by delta y, and that's the actual function doing that thing. So this approximation is only good for tiny little steps. Okay. Just want to show you a better drawing than what I was doing. Just basically any drawing. So what about, all right. So what we get then, let me see, can I connect that to this? All right. If I do, what is this going to be right here? Let me see. Come on, Jeff. The blue line is f of x, right? Blue line is f of x. What is that right there? What point is that? What's the input right here for this point? No. X plus delta x. And what does that make sense for? X is the one that we built the tangent line around, yes? X plus delta x is that step up from x, yes? It's how much the x changed. So what is this point right there? Okay, but what was the function again? It's f of x. So this, let me do this real quick. Let me just tell you. So this will be f of x plus delta x. This output, right? The input is x plus delta x, yes? So what will the output be? F of x plus delta x. Okay, love it. So this is just step up from x a little bit. The output's just going to throw the input into the function, right? So therefore, delta y is actually equal to that. Just basically what somebody else said a second ago. The change in y is where you started taken away from where you end up. That's how much the y changed. That's ground shaking, yes? Holy shit, Jeff. So isn't the change in y equal to y2 minus y1? Okay, I like it. And again, this is all built on stuff we know. We know this. We've known this stuff forever, but we're writing it in ways we're not used to. A little side note on this. What do I get if I divide both sides of this by delta x? Can you write that down? Go ahead and divide both sides of this by delta x. Okay. What was the connection between delta and d? Delta and d.
One's a little step.
Say again?
One's a little step and one's a
Good.
big step.
One is the smallest step you could possibly take, and the other one's something else, just whatever else, right? So I always call this a gross step. Not a gross misstep, but a gross step. D is the smallest possible step. So watch this. Does this look familiar to anybody at all? This almost looks like what, except one letter is kind of missing, sort of replaced. Yeah, shit. So if I do limits of both sides, as delta x goes to 0, if I apply that limit to both sides, what happens to these triangles? If I let this go to as small as it can be, the triangles become D's, because now they're the smallest steps possible. Equals, and of course this will just be the normal, I'm not going to try, Jeff. I'm not going to put all that shit in there, okay. Okay, all right. So just trying to make connections between the way we're writing things now versus how they relate to other things we've done. So I've got two ways to kind of approximate a change in y. I can either, well, this isn't really an approximation, this is straight up how much y changed. The approximation, all right, so I really want this to make sense. This guy is straight up, look at the function, where was it, where is it, take the difference. Right? That's what that is. How much did y change? Well, just look to see how much your elevation changed. Bam. Right? This, the approximation, is what we have up here. And when is this approximation better? When the steps are very small. Right? And again, why is that? Why do the steps have to be really small? Because what happens as I move along this function? What happens to the slope? As I move along this function, what's happening to the slope? The blue line. In this case, it's decreasing, but in general, it's changing. Right? So if I use the slope at a point, the minute I move, my slope is wrong. Does that make sense? That's another reason why it's got to be local. It's got to be really close, because the minute you move a little bit away, your slope is wrong. Okay, so let's do a concrete example. Do you guys want a concrete example of a problem you would see? I had a feeling. Okay, so let me rewrite what we just figured out. We have two ways of approaching this. One is kind of the exact answer, and the other way is the approximation using derivatives. Oops. All right. Where's my exact? Here we go. So let's say we're given, so here's an example. Given f of x is x squared plus 1. I want to know what delta, and I want to go from 1 to 1.1. So x goes from 1 to 1.1. I want to know what delta y is, and I want to know what dy is. What is delta x up here? 0.1, yes, because that's how much x changed, right? So what is delta y? It'll be f of what minus f of what? You could do it. What's x in this case? What's kind of like the beginning point? 1. I like it. So what is it? This will be f of 1.1 minus f of 1. And again, this yes.
Will delta x always be positive? So like if that were 0.9.
No, it doesn't have to be positive. It's a good point.
So
Yeah.
That 0.9 would delta actually be negative 0.1.
Yeah, if it said from 1 to 0.9, then delta x would be negative 0.1. I like it. Okay. So and again, it kind of pains me a bit. I don't intend to make this harder than it is, but isn't the change in y just f at one point minus f at the other point? Isn't that all that is? That's how much the y has changed on the function. So that you just throw in the old calculator, right? 1.1 squared plus 1 minus 1 squared plus 1, and you get something or other. 0.21, I like it. And the quick way to do that is, what is 11 squared? You guys should know. It's 11 times 11. 121. So what's 1.1 squared? 1.21. Yeah. 1.21 plus 1 is 2.21. 1 plus 1 is 2, so 2.21 minus 2 is 0.21. Okay, that's amazing. Okay, so what about dy? What do I need to know to figure out dy? Slope, I need to know derivative, right? So what is f prime of x? 2x. So now I can do, this will be dy will be f prime at what? What is x officially? Not thinking about delta x at all. X is 1. And what is dx? How much is x changing? 0.1. So the reason this approximation will not come out correct is because this is way bigger than infinitesimally small, right?
Why are we plugging in 0.1 for dx?
Say again, sorry?
Why are we plugging in 0.1 for dx?
Because how much did the x change?
Oh.
Yeah.
Okay.
So again,
Let's say for derivative of that.
no, it's the change in x, and which is normally a very small step. So that dy equals f prime of x dx will only be perfect when dx is truly infinitesimally small. Is dx infinitesimally small here? No. 0.1 is a huge step.
So is dx the same as delta x?
Roughly, yes. And the best we could do, if we're using this idea to approximate this change, the only thing I know for dx is delta x. So I'm using that as a stand-in. Dx means the smallest possible step over. And that's a really hard number to put in there, right? So I know this is not going to come out right, but this is going to come out close because 0.1 is not that very far away, especially because this function is nice. X squared plus 1, isn't that a nice function? Meaning it doesn't go like this, right? So 0.1 is not very far. What do I get if I do that? What is f prime of 1? 2 times 0.1 is 0.2. Is that close? Is that close?
Yeah.
Yes. Okay, I like it. All right.
That's it? That's like all?
That's it.
Okay.
Yeah.
You don't have to compare them or anything?
You can compare them. It
Well,
depends
I
on
mean,
what they
like,
ask.
do-
They can
do
ask
it-
you how far off was the approximation. Our approximation was off by 0.01.
Okay.
Yeah. Okay, maybe. So this is kind of like a building block. We're going to come back to this later to build other more complex ideas. This is just the very basic, what this shit to dy dx mean by themselves, how can they be used. And a lot of this stuff is stuff we've done before. We just didn't show it the way we're showing it right now. Okay, maybe. All right, we'll find out. Okay. So, 311. All right. I'm not going to spend a ton of time in here. 311, how do we say this? I don't know how to say this without people taking this wrong. All right, I'm not going to say it. What are normal trig functions based on? What would you say are normal trig functions based on? Don't say anything about triangles. What are normal trig functions based on?
Sine, cosine, tangent.
No, what are those based on?
Angle.
They use angles, but where do they come from? What's the first picture you see drawn normally for trig? Unit circle. So these are from the unit circle. Okay, I like it. In fact, what is the equation of the unit circle? What is the equation of the unit circle? X squared plus y squared equals 1, right? 1 squared. And of course, if we replace x with cosine and we replace y with sine, isn't this our basic first little trig identity, right? So let me see if I can say this word. I think I asked you this before. If you took pre-calculus, you should have done parametric equations. And when I said that last time, I had a lot of, like, what? Parametric equations. Does anyone remember anything about parametric? Okay, no. Okay, shit. Well, later this semester, I'm going to have a big review when we get to taking the derivatives of these crazy ass equations that we forgot, or maybe never learned. I'm sorry. Anyway, doesn't these together, if I keep putting in other angles, don't they kind of create the unit circle? Okay. So we say that these are parameters that define the unit circle. So normal trigonometry, that phrase will probably scare you because that probably means we're about to talk about some other kind of trigonometry. Normal trigonometry is based on unit circle. Okay. Hyperbolic trigonometry. All right, that should be kind of a giveaway. What is that based on, do you think? Hyperbolas. It's crazy. I like it. Oh, shit. So what is the... All right, this is going to be a really strange question. What's the difference between the equation of an ellipse or a circle and the equation of a hyperbola? Who remembers what the most basic difference is?
Plus and minus.
Yes.
Yeah.
Circles and ellipses have pluses, right? Hyperbolas have minuses. Now listen, this is so cool. I have no idea how you were taught about this, but ellipses and circles, would you agree with me that they're closed?
Yeah.
So they can only go so much in any direction, correct?
Yeah.
So if I said the square of two numbers adds to be 9, aren't there like an infinite number of things that do that?
Yeah.
But if x gets bigger, doesn't y have to get smaller? So, okay, so they're closed. If I do x squared minus y squared, so tell me this. Well, let's start off with this. If I just do x minus y, can somebody give me two things that x minus y equals 2? Give me 2, an x and a y.
5, 3,
Yeah, so let's just do 5 and 3. It's crazy. Give me something else.
4, 3 and 1.
3 and 1. What about 20 and what?
18.
18. Holy shit. What about 2 million? How about 2 million and 2? And 2 million, yes? Are they closed? Are they bounded?
Yeah. Wait.
What's happening? Can they get as big as they want to?
Sorry. Yeah.
Yes.
Yes, as long as the other one also gets big, because it's subtraction, right? Addition, if one gets bigger, the other one's got to get smaller to keep it equal to that number. Subtraction, they can go insane. I really want this to make sense. That's why ellipses and circles look the way they do, and hyperbolas go crazy. Can x and y get closer to each other than 2? In fact, they have to be 2 apart, don't they? Which is why there's no middle part. They can't get close. They must stay a certain distance apart. Okay, maybe. So when I teach circles and ellipses, I like to point out, because of the plus, it makes sense they look closed. Hyperbolas look open for the same reason, because it's minus instead of plus. Okay, maybe. So hyperbolic trigonometry is based on kind of like what you could call the unit hyperbola. So it's just like a circle equation, just with a minus in it. Okay. All right, now. All right. Teaching this is really interesting. I'm going to come back to this in a minute. I just want to lay the groundwork for what this is going to mean. Now, let me throw at you some seemingly unrelated stuff. And of course, it's going to come back and relate. So what if I have a function e to the x plus e to the negative x over 2? Is that all right? If you had to do a derivative here, would you freak out or would you go, okay? Yeah, it's got e's in it. It's got to be relatively easy, right? And let me call another function, I don't know. That.
Is that a y?
Sorry. My x's keep looking like y's. Nothing freaky going on, guys. Sorry. And this is a x also. Sorry. Can you guys... All right. Can you guys please figure out what f of x squared is? I'll wait. Let me just tell you, I mean, I would write this like this, but you might want to break it up, or you might want to, it's up to you. I would do this. So you don't have to worry about the 2 anymore, right? So what do you guys get? Let's see. Anybody get that yet? Either the 2x.
Plus 2.
Good, because this times this is 1, and you get 2 of them, right? Is that cool? E negative x times e to the x is e to the negative x plus x is e to the 0 is 1. And you get that twice for the middle terms. Yes?
Plus e to the negative 2x.
I like it. And then what I did for you is I did the same thing for g. I don't know why I'm writing them like that, but I just am. So what is g of x squared minus f of x squared?
-1.
Did I turn those around? I did. Shoot. Sorry. Do this. F of x squared minus g of x squared. Sorry.
1.
Yeah. So it'll be, won't it be, if we kind of write this out better, this will be e to the 2x over 4 plus 1/2 plus e to the negative 2x over 4 minus, right, that's f, minus e to the 2x over 4 minus negative, so plus 1/2 minus e to the negative 2x over 4. So this shit cancels, this shit cancels, I get 1. All right, so this feels like, some of you guys probably see the connection now, but this feels a little disconnected from what I was just talking about, maybe, right, with the hyperbola stuff. But what we just figured out is, if I replace x with this and y with this, then they describe this hyperbola. The same way that replacing x with this and y with this describes the unit circle when you add them. So we're not going to suddenly do a whole other 2 weeks on hyperbolic trigonometry. Holy shit. But I just want to show you how these do relate to hyperbolas the same way normal trig functions relate. Now I keep saying trig functions. So let's improve this a little bit. Let's call this cosine somehow, but not, it can't be cosine, right? So let's call e to the x plus e to the negative x over 2, let's call that hyperbolic cosine, affectionately known as cosh.
Cosine.
Huh?
Cosine.
Cosine, exactly. It's the cosine. And then, of course, incredibly enough, what would we call this? What do you think? So why do I call this cosine? Because it's what replaces the x. So what am I going to call this one? Sinh. Or sinh. All right, so this is sinh because it replaces the y. So this is the formulas for these. Okay, there's a lot of other neat. Now, obviously, could I make tanh? What would tanh be? Tanh would be pretty easy. What do you think tanh should be defined as? What is tangent? It's defined as sine over cosine. There it is. So what's tanh? Sinh over cosh. So then the 2's would cancel, so you get this over this, yes? That would be tanh. What would cosec be?
1 over 6.
Yeah, 1 over this. So it'd just be this thing, right? Are you guys kind of with me?
What's the H from?
H stands for what?
Hyperbolic?
Hyperbolic, yeah. So if you look at your calculator, don't you see sine and don't you see sine H on your calculator, if I remember correctly? No? Oh, that's on this. I'm thinking about, all right, let me show you. So this is this one. I feel like I'm going to pull like a lamppost out here. Do Mary Poppins stuff. No, that doesn't even have it. What am I thinking about? Oh, okay. Let me show you this one real quick. If you have a little, see right there?
Oh,
Isn't that neat? On this one, let me see if I remember where this is. Let me see if I even. This would have been like a good teacher thing to do, would be to go and do this before, but oh well, we're going to do it live. We're going to do it live! I actually don't remember where my hyperbolic stuff is, and I just want to capture it here for all eternity that I've forgotten this. It's got to be, well, I know it's under catalog, but that's sort of cheating a little bit. Should be here. Like there's Kosh. There's Kosh under the catalog, but why can't I remember? I really can't remember.
okay.
Where'd you find it? Did you find it in a?
No, it's in
Yeah, I'm not seeing it anywhere else.
Yeah, me either.
All right, but here's a quick way to get it, and then I'll look it up. I forgot where that. There should be a way to just get it directly, but I can't at the moment remember. But if you go, there's a really cool button. See right above 0, it says catalog. So if you hit second 0, it tells you everything the calculator can do. So if I want Kosh, I can go see where the button that has a C over it. If I click this button, I go to the C part, and then I can go down to Kosh. Weehaw! All right, there's got to be a quicker way to do it, though, so I got to look that up. I forgot to look that up. Okay.
You're telling me you don't know every single thing that the calculator does? Wow.
I'm sorry. I'll retire now. I always said I would retire if I can't read my own writing, but maybe there's another condition. Okay. So the homework, all right, do this for me. Let's look at some calculus. This is not calculus, by the way, is it? This is not calculus. You could have learned this in pre-calc. But, you just didn't want to overload you. Pre-calc is already loaded down with a lot of shit. Do you guys remember? Agree? Pre-calc is one of our most dense classes. There's just so much shit in there. We're like, nah, let's not do it. Figure out what this is. Figure out what this is. It's not me off for sure. It's a hyperbolic cosine stuff. So you all sound drunk. So go for it. Really careful. All we know at the moment is the basic definition of hyperbolic cosine, which is what? And real quick, I don't think this is a stretch, but remember how cosine's an asshole? I want you to realize something. See how sine is like, okay, that's a positive power, so this is positive. That's a negative power, so this is negative. Oh, sine's all like, want to be nice, and cosine's like, everything's positive because I want out. Anyway, sorry. I might be pushing my analogy a little bit. Too bad for you. I like it. So then this is how I do this guy's derivative. Now don't think freaking quotient rule. That's insane because this is just this, right? Yes? So no quotient rule. The bottom's a constant. You never do quotient rule if the bottom's a constant. So what do you get? What's the derivative of this? What's the derivative of this? Yes, it'll be 1/2 e to the negative x times the derivative of negative x is -1, so it'll be minus. Isn't that, what is that? No. Oh, sorry, you can't see anymore. What is that, the definition of? Sinh. You're okay, dude. I'm not going to come down on you because we just learned this shit. Sinh is the nice one. Negative, so I'll put in negative, and Kosh is the asshole. This makes it plus no matter what. So that's different, isn't it? Because what is the derivative of cosine? Negative sign. I like it. So we should expect this to be not exactly the same as normal trig, but it is set up exactly like trig is set up based on circles. This is based on hyperbolas, where relationships are not going to be exactly the same. Okay. All right. And just to give you some general uses for this, has anyone ever been to St. Louis? The arch was actually designed to be a hyperbolic cosine function. I don't know if that makes it worse for you guys. You're like, I liked it, but now it's kind of like, I don't want to look at it anymore. There's also things called catenaries. Do they have a picture of that? Oh, there it is. So when you have a rope or like a telephone wire or something, or hanging between two things, the shape they take on is called a catenary, and it's defined by hyperbolic cosine. So here's what hyperbolic cosine looks like, and here's what, well, where's sine? Sine looks more like a tangent, sort of. Where'd you put sine? There it is. Hyperbolic sine is this red line. Hyperbolic cosine is this. Okay, maybe. Freaky. But the problems, you guys doing okay out there? I mean, if I graph e to the x plus e to the negative x divided by 2, I get this. Because here's e to the, yes? Isn't this exponential? Yes? Isn't this with a negative power exponential? It would just flip. And then what do I get when I add those? I get this. Isn't it going to be the smallest down here, and then it's going to add together to be up here? Okay, that's all. And then the same thing happens with sine, but the sine is going to be a difference between the two. Well, sinh, I should say. Should say. Yes?
So the e to the x plus e to the negative x over 2, that isn't like an arbitrary number, that's a specific number for cosine h x?
Well, I mean, you can plug in anything you want to figure out what the hyperbolic cosine of something is, right? So if I want to know what the hyperbolic cosine of 7 is, I would just put a 7 in for x.
Yeah, but it's like, with the way it's set up, it isn't arbitrary. Like,
no.
It's a specific... Okay.
That is what the hyperbolic cosine is defined to be.
Okay.
Right? Just like our cosine x is defined to be the ratio of two sides of a triangle, right? It's got a definition.
Yeah.
Right? Okay. Same thing here. Yes?
How did you figure that out?
They didn't have Facebook, they didn't have Instagram, they didn't have TikTok, they had candles and paper and quills. So they just sat there and did this shit. Why not? They were bored, right? So I don't know. That's maybe the drunk history of that. What else was there to do besides play with my exponentials? That's not a euphemism. Let me see. That's it. Yeah. All right. You just got to try the stuff out. I'm not going to make you memorize a damn thing about hyperbolic. You do have to do the homework. So, for example, here are the inverse hyperbolic derivatives. Do they look a little familiar?
Yes.
Yeah, holy shit. Here's what they look like, the inverse hyperbolic functions. Of course they have natural logs because the functions themselves are based on e. Do you have to memorize this? No. Do I have this memorized? Shit, no. All right. But what I always hate is when I'm teaching a higher level calculus and I say hyperbolic stuff, and this is where, and people look at me like, never. Now you guys have heard of it. You guys are going to do homework about it. So if you take any further math classes, you'll know it when you see it. And even if you don't see any further math classes, you'll be able to do some problems I give you. Yes?
So we're arguing 9 through 11 as well as all of chapter 4 through chapter 5?
Yes.
Okay.
Well, yes. Because 9, we had a very basic problem. So in the next test, I'll have a more complicated 3-9 problem. There'll be linear approximation differentials. There will be hyperbolic stuff. Yeah, this next test is going to be exciting. Okay, now, last thing for today. Who knew calculus was going to be hard? All right. This, I've been sort of getting us ready for this for a while now. And in fact, I basically directly said this last class, I think. If I have a function, let me just try it this way. What if I want a function? Well, let me see. How do I say this? Okay. Does this make sense that this function has, let's say, a couple things? Does it make sense for me to say this function has a local maximum at x equals a? Now, I really want this to make sense. Is this the maximum of the function? Is that output the maximum output that function gets? Hell no. Right? It goes higher. But isn't this a local maximum? Right? Sort of like you climb a hill, you see another hill that's taller, but you're like, I'm locally high. Well, that's again, that just goes along with the theme of today. I'm not sure. Say something that could be taken many different ways. All right. And of course, what would I call this? So there's a local max at x equals a. What would I say about x equals c? Local min. Holy shit. Now, what can I say about this one? Yeah, so there's an absolute min at x equals b, right? But it's also a local min, isn't it? Because a local min has no idea what's happening anywhere else. So a local min could be the absolute min. Absolute min and local min. Okay. Become a thing. There we go. Is that the only... Now tell me this. What is true at each of these points? Slope is 0. I like it. Does the slope have to be 0 for there to be a local max or a local min?
Yes.
If you say no, give me an example. We know an example. Come on. There's a beautiful example that's got a local min that is definitely not differentiable at that point. Yes. Is it differentiable here? Is that the local min? Hell yeah, it's a local min, isn't it? Locally, it's the lowest value output for the function. It's also absolute min, by the way, right? But if I did this, then it's just a local min, yes? I get the m function. So there is definitely a local min here, but f prime, I'm trying to make that 0. F prime of 0 is not 0. It's undefined. So what's kind of a general thing we can say then? Where might there be a local min or a local max? What has to happen there if there might be a local min or a local max? Either the derivative is 0 there, or the derivative is undefined there. I love it. So let me ask you this. So, by the way, did you guys pick up on the fact that I just said there might be? So, for example, is the slope at 0, 0? Really? Right? And what is this function, by the way? Let's just pretend like it's definitely this. This function is x cubed, yes? What's the derivative of x cubed? 3x squared. What's the derivative at 0? 0, yes? Is that a min or a max here? Is it a minimum? No. Is it a maximum? No. So it's neither. So that's why I said they can only occur where the slope is 0 or undefined, but they might not happen there either, right? I want this to make sense. Maybe? Because what did this do? Doesn't this is one of those like, oh, I'm going to turn, no, I didn't, so it looks like it's going to turn. If it turned, it would be a max, yes? Or look at this way, if it turned this way, it would be a min. But it just didn't do either one. Nah. Okay, so we've been so getting ready for this. So what do you think I should call, well, no, I could get all kinds. Any point, all right, let me say this. For a given function, if f prime of c is 0 or f prime of c is undefined, we call c, f of c, a critical point. So at some x equals c, if the slope is 0 or the slope is undefined, that is a candidate for max or min. When would it not be either if it sort of fakes this out? So haven't I given you problems that got you ready for this? Haven't we done problems where I said find where the horizontal tangent line for this function, right? Where you take the derivative, set equal to 0, you blah, blah, blah. We were collecting critical points. We just didn't call them that yet. I do. Okay. I was trying to remember if I had a, what do you call it? I do. Let's do one example together. I'll give you this handout. We'll do a little bit of the first problem. We'll call it a day. All right. So for f of x equal to 4x plus 1 times 3x minus 2 squared. Let's find the critical points. That's interesting, Jeff. Put the instructions over there. That makes so much sense. Part A is find the critical points. So what do I do then? What's the first thing I do? Take a derivative. Yeah. All right, so let's see what we get. Wouldn't it be derivative of this guy, right, times this guy? Let's see if I can get away with breaking my own suggestion. I'm not going to write the rule down. We're just going to go for it. Plus this guy times what? Derivative of this guy, which would be what? Yeah, so the 2 comes down. Times 3. Damn you. Instructions. I really want everybody, is that cool? 2 came down, times this to the first, times the derivative of the inside. Can we stop for a minute? So now I got 2 times 3 is 6. By the way, real quick, this, I'm glad I'm remembering this right now. Can I put 2 times 3, 6? Can I put that over here with the 4?
Yeah.
No.
Hell no.
Why not?
Hell to the no. So why am I allowed to put 2 and 3, 6? Why am I allowed to put it right there? Because what's the only operation happening right here? Multiplication. What is happening right there? Right?
Yeah.
Okay. Never do that again.
Sorry.
That's okay. That's okay. I know. Okay. Can I find my critical points right now? Is this factored yet? Okay, that's the answer to the question. Then no, you can't find the critical points yet because you haven't finished factoring the damn thing. How do I factor this? What number comes out? 2. How many of these come out? 1. Can I take any of these out? No, he doesn't have any. So what's left? 4 divided by 2 is 2. I had 2 of these. I took one out. Right? Just a little better, Jeff. Plus 6 divided by 2 is 3. I took this out, so I'm only left with this. Yes? And then I get 2 times 3x minus 2 times 6x plus 12x is 18x. Minus 4 plus 3 is minus 1. All right, let me stop for a minute. Is that cool? Right? Doesn't this feel familiar? Haven't we done several of these kind of problems? And now you set it equal to 0. And what do you get? 2/3 and 1/18. I like it. Now, what do we know right now? What do those mean? What are those? Critical points, critical x values. I like it. Critical x values. Are they maxes or mins? We don't know. Right? So now we got to come up with a way to test them. Okay, so think about this. Let me see how much time I got. Like none. So if it was a maximum, what's the slope here versus the slope on the other side? Slope here is positive. So it kind of makes sense. If my critical point on one side the function is coming up and the other side is going down, it's got to be a maximum, doesn't it? And vice versa, right? So I have no room for this, but let me see. I can do this. Isn't this derivative 0 there and there? Yes? You're like, yes, Jeff. Let me put 0 down there. Here's 1/18. Here's 2/3. Oh, this is gross. It's too bad for all of us. So this is where some neat things. If I say the word multiplicity, does anyone have any idea? Multiplicity. Multiplicity? It's a really cool movie with Michael Keaton, by the way. But it's also mathematically, what does multiplicity relate to? Does anyone remember? It's whether or not the function would turn or go through. Anybody? Remember that? A little bit? Okay. See how these are both multiplicity odd, which means they're going to go through? All right. We're going to have to really do some more stuff next time, but all right. Let's do this. Before I do what I'm about to do, we're going to have to review multiplicity because it's going to help us out a ton. So let me give you this. Bring this back with you next time. And we're building our way up to doing these here. You could actually probably do the first couple in the first row. So that's enough for today. You can kind of see. By the way, real quick, I just said that phrase. I know. I like doing this for you on a test or a quiz. In case you can't get the derivative to work, you at least know what it's supposed to be, so then you can do the next steps. Does that make sense? So I'll say or show that or verify that the derivative is this. So if you can't do it, you'll just lose points on that one thing. You'll be able to do the other problems. Okay. All right, that's enough, guys.